An A36 steel bar is made from two segments having cross-sectional areas of 1 square inch in section AB and 2 square inches in section BD. What we need to do is determine the vertical displacement at the end, point A, and the displacement of point B relative to point C. And this is A36 steel, so we're assuming that we have a modulus of elasticity of 29 times 10 to the 6th psi. So we're going to use our deformation is equal to the sum of the PL over AEs to solve this. First thing that we need to do, though, is we need to calculate out those internal loads. So let's first of all take a look at our bar and find out how many different internal loads that we have. So now if we remember from mechanics, statics, internal load is going to be the same until an external load is applied. So I'm going to do here. Once that 4 kips comes into play, the internal load is going to change. And then once these 8 come into play, it's going to change again. So let's draw free body diagrams for each of these. So I'm going to start with the first one. And I'm going to have a 15 kip force on that top. Then I come down here to the second one. I have something basically shaped like this. I'm going to have 15 kips pulling one way. And then I have, oops. Sorry, that got a little bit bigger. Let me redraw this too. This is a long thing in 2B. And then I have 4 kips. Now, this is going to be this is 2 forces of 4 kip each, so a total of 8 kips. And then we'll have some internal force. And then lastly, we come down to this bigger one with this ring on the end for the last. So I've got 15 kip this way, 2 4 kip forces, and then 2 8 kip forces. Now, I could draw a free body diagram, and I could figure out what the reaction force here at D is, and I can work it the other way. It does not really matter. You're going to end up with the exact same thing no matter how you do it. So let's take a look at what the internal forces are, because we have to have the internal forces. So this first one, they're all in static equilibrium, which means the forces have to balance. It can't move. That is a 15 kip internal force pulling away, so it's in tension. So that is showing this piece in tension, so we're going to have a positive deformation. So if I look at this next one, I have 15 kips going this way. I have 8 kips going down. To have everything balance out, I need an internal force of another 7 kips pulling this way. Once again, I've got it in tension in this part, since I'm trying to elongate it. So between B and C, that's a positive deformation. Now in this one here, I've got 15 kips going this way. I have 8 kips pushing down. I have another 16 kips pushing down. So the only way that's going to balance out is if I have an internal force of 9 kips going this way. Now this one's in compression, so the deformation is going to be shrinking on that. So positive in the first section, positive in the second section, negative in the third section. Okay. So let's go and actually solve that. So our deformation is going to be the sum of all the PL over AEs. And so then what we have is, okay, well, that's going to be PL over AE of that first section. And that first section that we put together is from A to B. And then we're going to do PL over AE from that second section, and that's B to C. And then finally, PL over AE from C to D. Now, I'm not going to factor out the E's, since we do have E in all of them. And the reason I'm not going to factor it out is because I want to know what the deflection between each point is. So that way, it makes doing the deflection between B and C, this guy right here, because that's the second part of our problem, it's going to make it a little bit easier. So the deflection at A. And technically, if you want to write it, you can write it the deflection between A and D. with the slash, or you could just write the deflection of AD, or you could just write the deflection of A. It doesn't really matter. And so PL over AE. So that first one's 15 kip. That's our load. And that is thousands of pounds. So you can write in kip, or you can write in 15e to the 3 pounds. Now that's over a length. And so remember, if we go back, that internal force, it's over the length the internal force acts. It's 15 kips from point A, doesn't change till point B. So it's acting over that entire 2 feet. So that is going to be our thing. It's going to be 2 feet. Now, that's given in feet. Everything else we have is going to be in inches. So I am going to convert that, and I'm going to say that I have 12 inches for every 1 foot. And so that feet will cancel out. I've multiplied it by 1. I don't change the equation. Divide it by its area. Its area is 1 inch squared. And then it's 29 times 10 to the 3 kips, KSI. So that's 23 times 10 to the 6th PSI. Because remember, a KSI is thousands of pounds per square inch, so we're just going to convert that to PSI. That's A to B. Let's do B to C. And so I have 7 kips, or 7 times 10 to the 3 pounds. That one acts over 1.5 feet. And then I'm going to convert that 12 inches by 1 foot. Divide that by the area, 2 inches squared. Same modulus of elasticity, 29 e to the 6 psi. So the last one I'm going to add to it is that last one is 9 kips of compressive force. So negative 9 times 10 to the 3 pounds. It's only acting over a foot, but we also need to convert that to 12 inches as 1 foot. 12 inches is 1 foot. I'm going to divide that by its area. It's also 2 inches squared. And it's also 29 e to the 6 psi. So now if I go and I bash all those numbers together, the deflection at point A should be 0.0127 inches. So there's the deflection of A. Second part of the problem says that, so I'm just trying to, I want to change my pen color here. So this is positive, which means that it's growing, so it's getting bigger. So the second one is I want to know what the deflection between points B and C are. So how do I do that? I've already calculated that out right here. It's that section. So if I go and I calculate that out, 0.0217 inches. Now, this is still elongating because it's still a positive number. And so that's how we use deformation to calculate out how large bars are going to be.